Imagine standing just a few feet away from a river of fire. Not lava from a volcano, but molten steel, glowing brighter than the sun at over 1,500 degrees Celsius, flowing through channels inside a factory the size of a small city. That blazing liquid will soon become the backbone of skyscrapers, the skeleton of bridges, the invisible strength inside stadiums, airports, and megastructures across the world. But how does raw rock pulled from the earth transform into perfectly engineered, massive steel beams strong enough to hold thousands of tons? Today, we're stepping inside modern factories to follow that journey, from stone to fire, to the towering beams that literally hold up our world. It all begins far from the factory floor. Deep in the earth, iron ore is mined, reddish rock packed with iron oxides. Giant excavators scoop it from open pits. Massive crushers grind it into smaller pieces. Conveyors carry it across processing plants where it's cleaned and prepared. But iron ore alone can't become steel beams. It needs transformation. At the heart of a steel plant stands a structure that looks almost like a launch tower, the blast furnace. It can soar more than 30 meters high and operates non-stop for years at a time. Inside, iron ore is layered with coke, a carbon-rich fuel, and limestone, which helps remove impurities. Then comes the heat. Superheated air blasts into the furnace at temperatures exceeding 1,000 degrees Celsius. The coke ignites. Chemical reactions begin. Temperatures rise above 2,000 degrees Celsius. The iron ore melts. Impurities separate and float upward as slag. Beneath it, molten iron collects glowing white-hot, dense, and powerful. When tapped from the furnace, it pours out in a stream of blinding orange light. This is pig iron, strong but brittle, not yet ready to support a building. To turn it into steel, it must be refined. The molten iron moves into a massive vessel called the basic oxygen furnace. Here, pure oxygen is blasted into the liquid metal at supersonic speed. The reaction is violent. Sparks erupt like fireworks. Flames shoot upward as excess carbon burns away. Within minutes, chemistry reshapes the metal's entire structure. Engineers carefully monitor carbon content, adding alloying elements like manganese or chromium to adjust strength and flexibility. When the process ends, the liquid inside isn't iron anymore. It's steel, engineered to exact specifications. But it's still molten. To shape it into something solid, something structural, the steel flows into the continuous casting system. Imagine a vertical mold, cooled by circulating water. The molten steel pours in from above. As it descends, the outer layer solidifies first, forming a thick shell. Inside, the core remains liquid for a short time before fully solidifying. The strand of steel emerges as a massive rectangular slab or billet, glowing red as it moves along rollers. These slabs can weigh several tons. They're solid now, but they still don't resemble beams. That transformation happens in the rolling mill, one of the most dramatic parts of the entire process. The slabs are reheated to around 1,200 degrees Celsius until they glow bright orange again. Then they're sent through a series of colossal rollers. Each set of rollers compresses and stretches the steel with tremendous force. With every pass, the shape evolves. First, the slab becomes longer and thinner. Then specialized rollers begin forming the distinct geometry of an I-beam. Wide flanges at the top and bottom connected by a central vertical web. The shape isn't random, it's engineered brilliance. The flanges resist bending under heavy loads. The web handles shear forces. This configuration allows beams to support enormous weight while using less material, maximizing strength and efficiency. As the beam races through the rolling line, sparks fly. Steam bursts into the air. The ground trembles slightly beneath the machinery's power. In a matter of minutes, a glowing block of steel becomes a precisely shaped structural beam, stretching dozens of meters long. But the journey isn't finished. The freshly rolled beam is still extremely hot. It travels onto a long cooling bed, sometimes over 100 meters in length. Here, it cools gradually in open air. Cooling must be controlled carefully. If it cools too quickly, internal stresses can form. Too slowly, and production slows down. Modern factories use thermal sensors and computer systems to monitor temperature across the entire length of the beam. As the beam cools, it loses its orange glow and darkens into solid steel gray. Next comes straightening. Even the smallest curvature matters in structural engineering. Massive mechanical straighteners apply calculated pressure to remove any bends or distortions. Laser systems measure alignment down to millimeters. Precision is everything. After straightening, beams are cut to required lengths using powerful saws or oxygen-fueled torches. Some are drilled with bolt holes. Others are coated with protective layers to guard against corrosion, especially if they'll be used outdoors or in marine environments. Then comes quality control, the final test before shipment. Samples from production batches are pulled into tensile testing machines that stretch the steel until it breaks. Engineers measure yield strength, tensile strength, and ductility. Ultrasonic testing scans for internal cracks invisible to the naked eye. Magnetic particle inspections reveal surface flaws. Spectrometers verify chemical composition. Only beams that meet strict structural standards are approved. Because these beams won't just hold steel and concrete. They'll hold people, families, entire cities. Once approved, the finished beams are loaded onto specialized transport vehicles. Some measure over 30 meters long and weigh several tons. Escort vehicles guide them through highways. Cranes lift them into place at construction sites. High above the ground, bolted and welded together, they become part of something far greater, the framework of a skyscraper, the spine of a suspension bridge, the structure of a massive warehouse. From a distance, we see glass, lights, and architecture. But hidden within is steel, forged in fire, shaped by force, refined by science. Massive steel beam manufacturing is a blend of raw power and microscopic precision. It combines chemistry, physics, metallurgy, automation, and engineering on an industrial scale. Thousands of tons move daily through these plants. Rivers of molten metal flow continuously. Machines apply pressure strong enough to reshape solid steel like clay. And yet, the final product must meet tolerances measured in millimeters. That balance between extreme heat and careful control, between brute force and engineered precision, is what defines modern steel manufacturing. The next time you stand beneath a towering building or cross a long steel bridge, imagine the journey hidden inside those beams. From rock mine deep underground, to molten fire inside a blast furnace, to glowing slabs rolling under crushing pressure, to perfectly straight beams lifted into the sky. It all begins with a spark and ends as the silent strength holding up our world.